Well, hello friends. In this video, I will be discussing on the topic of Gibbs state or the thermal states. So this is the first topic for discussing something that is close to thermodynamics point of view. So we already have seen noisy operations and how they are implemented by using the free states, which are the maximally mixed states. Now, and also one of the important point is noisy operations, they are unital or they keeps the maximally mixed state unchanged. And along with the fact that entropy of any state is actually bounded above by the entropy of the maximally mixed state, we can say that in this noisy operation, what it says is that in an isolated system, entropy or disorder always increases. Because you see, the free operations of noisy operation are unitary operations and they can keep the entropy same, but the partial tracing is a loss of information that is here and that can increase the entropy. So given a state rho, it undergoes the transition to rho s, and then it can go to rho s double prime. Like that, it can maximum reach I by d. But it cannot go any further because this has achieved entropy maximization. So here we can see one of the laws of thermodynamics coming into play, that entropy maximization must be there. But it is for a very restrictive system where we have not introduced anything like bath or system and reservoir and all those things. So now we consider a more general state, that is this state. Now this state is called Gibbs state. We will see why. So this state is characterized by a particular parameter beta, which is a scalar quantity, and it is denoted as e power minus beta times the Hamiltonian of the system divided by a function z beta, which is the normalization of this state, that is trace of e power minus beta h. So this is trace of e power minus beta h. And now and the Hamiltonian can be in any dimension. It can have terms like E1, E2, E3 like that. Here I have shown a 2-dimension in Hilbert space of 2 dimension that has only E1 and E2. So, but the important point is this trace of this state, Z beta that we are denoting, it is almost similar to the what is called the partition function in statistical mechanics. Now let's see a bit more of this. First of all, if the Hamiltonian is degenerate, that is all the states are same, like E1, 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 then we see this state, this Gibbs state that we have here, it reduces to the maximally mixed state. But now this means that it is incorporating the fact of the noisy operation within itself. But now let us consider what is the entropy of this state, this Gibbs state that we have written. So now for this we will work in 2 dimensions, but it can easily be generalized in several dimensions, finite dimensions. So the Hamiltonian is degenerate, non-degenerate, E1 and E2. And then what is the Gibbs state? It is e power minus beta h. So this will exponentiate to give this and this term, and then I have 1 over z. This z is taking care of the normalization of this thermal state such that trace of tau beta is 1. Now let's move on. So this is the z here. Now we have not made any connection that beta is 1 over kbt. This is something that we have not even made. We have just said beta is a parameter. So with this much, we can now start calculating the von Neumann entropy of this state. So it is minus summation lambda I log lambda I. We already know that these are the lambda I with 1 over z factors with them. So that I have written in this part and in this part. Now we can just simplify the entire thing, and at the end what we get is the system, the von Neumann entropy of the state, which is the Gibbs state. It is of this form that I have written here. So now you see this form is very similar to when you see this form that we have obtained of this Gibbs state. It is actually quite similar to the fact that when we say minus beta f equal to ln z, where f is the free energy, and then we say f is also equal to u minus ts, and then this relation gives a relation between s and ln z. So this is the relation that it gives, but we have not made use of any thermodynamics, but we are still arriving at this relation. Just by using this state, we are seeing that the entropy of this state is precisely the entropy that we talk about. But now we can move further by incorporating the Klein's inequality. So Klein's inequality says that the relative entropy is always greater than or equal to 0. So we can take one of the state to be the Gibbs state and another be any arbitrary state. So that arbitrary state will have some probability distribution which is diagonalized in this fashion with P1 and P2 values. Now I will just need to plug that in this part, and we'll start simplifying this matter. So this simplification is also quite simple, but what result that it gives is that in the last line you see E1 P1 plus E2 P2. This is the average energy for this state rho, which has P1 and P2 as its values, as the eigenvalues. And so this is the average energy, and we see that we are getting an inequality. We are getting an inequality where we see this side. This side is precisely the expression. This side is precisely the expression of the entropy of the Gibbs state. That is here. So you can compare this expression and this expression are same, provided that the average energy here and here are same. The average energy here, so average energy by definition is of this form. So average energy of any system is trace of rho times the Hamiltonian. So average energy here is the average energy of tau, average energy here is the average energy of rho. But now we consider such a system which have a constraint that average energy remains same. This is what happens when a system is connected to a thermal bath that we have always discussed in statistical mechanics. So when a system's average energy is constant, under constant average energy, we see that the Gibbs state has maximum entropy. The Gibbs state has maximum entropy corresponding to in regards to any other state. And hence we see that in this formalism, we will see that any state rho, it tries to equilibrate to this Gibbs state so as its entropy can be maximized within the constraint that it is connected to a bath and hence has a constant average energy. And this is the essence where we see the laws of thermodynamics evolving from the resource theory and information theoretic perspective. The beta parameter here, we can say that we can define temperature to be 1 over the beta parameter, and hence we are not incorporating any temperature and yet we are getting some sort of a parameter. So this is in a sense the essence of the zeroth law, the fact that the temperature function, such a function of temperature exists. So that's all for this video. In this video we discussed mostly about the Gibbs state, the fact that the entropy of Gibbs state is of this form and that this entropy is the maximum under the constraint of constant average energy. So in the next video we will lay down the rules of thermodynamic operations and how they are resource theory.